What you're seeing are individual atoms, captured using a machine that shouldn't work according to classical physics. The electrons creating this image are tunneling through barriers they don't have enough energy to cross. It's impossible, yet here it is. Every second, your phone performs a billion impossible acts. Electrons teleport through walls of silicon dioxide, storing your photos, texts, and this very video. This is the Schrödinger equation, the mathematical reason why the impossible happens every day. In the next 20 minutes, we'll explore how a formula that describes the fundamentally unknowable became the foundation of everything we can know about modern technology. The quantum crisis of 1925. Picture this. It's 1925, and physics is in complete chaos. Scientists have discovered that electrons orbit atoms in discrete energy levels, but classical physics predicts every atom should collapse within nanoseconds. Here's what makes this crisis profound. If classical mechanics were correct, you wouldn't exist. Neither would stars, planets, or any stable matter in the universe. Enter Erwin Schrödinger, Austrian physicist, philosopher, and reluctant revolutionary. Inspired by Louis de Broglie's matter-wave hypothesis, Schrödinger set out to find the fundamental equation governing quantum systems. But here's the irony. When Schrödinger first derived his equation, he initially rejected it. The mathematics seemed too strange, too removed from physical intuition. He famously said, "I don't like it, and I'm sorry I ever had anything to do with it." He was wrong about his own Nobel Prize-winning discovery. Deconstructing the equation. Let's decode what might be the most elegant equation in physics. The time-dependent Schrödinger equation is I times h bar times the partial derivative of psi with respect to time equals h hat times psi. Every symbol here represents a fundamental aspect of reality. This I is the imaginary unit, the square root of -1. Yes, the equation describing reality fundamentally requires imaginary numbers. This isn't mathematical trickery. It's telling us that quantum mechanics operates in complex mathematical spaces that classical physics never explored. H bar is the reduced Planck constant, h divided by 2 pi, equals 1.055 times 10 to the -34th joule seconds. This tiny number sets the scale where quantum effects dominate. If h bar were larger, you'd quantum tunnel through chairs. If it were 0, we'd live in a purely classical universe. Psi is the wave function, the most mysterious entity in physics. It doesn't tell us where a particle is, but rather the probability amplitude of finding it anywhere. The wave function contains every possible future until the moment of measurement. H hat is the Hamiltonian operator, encoding the total energy of the system. The Hamiltonian equals T hat plus V, where T hat equals P hat squared over 2m, representing kinetic energy, and V represents potential energy. In position representation, the momentum operator becomes P hat equals -I h bar times the gradient operator, so our kinetic energy operator transforms to T hat equals -h bar squared over 2m times the Laplacian operator. This is why the position space Schrödinger equation contains second derivatives. They represent kinetic energy. The time-independent form and energy eigenstates. For systems with time-independent Hamiltonians, we can separate space and time variables using psi of r and t equals phi of r times t of t. Substituting into the time-dependent equation and separating variables yields h hat times phi of r equals e times phi of r. This is the time-independent Schrödinger equation, an eigenvalue problem where phi of r are energy eigenstates, e are energy eigenvalues, and solutions form a complete orthogonal basis. Consider the simplest quantum system, a particle in a one-dimensional box. The equation becomes -h bar squared over 2m times the second derivative of phi with respect to x equals e times phi of x, for 0 less than x less than L. With boundary conditions phi of 0 equals phi of L equals 0, the solutions are phi sub n of x equals the square root of 2 over L times sine of n pi x over L. The energy eigenvalues are E sub n equals n squared pi squared h bar squared over 2m L squared, where n equals 1, 2, 3, and so on. This reveals quantization. Energy can only take discrete values. This isn't imposed by hand, it emerges naturally from the boundary conditions. Quantum tunneling and semiconductor applications. Now for the phenomenon that powers your digital life, quantum tunneling. Consider a particle approaching a potential barrier. The potential V of x equals 0 for x less than 0, V naught for 0 less than x less than a, and 0 for x greater than a. For energy E less than V naught, the solutions in each region are region 1 where x is less than 0, psi 1 equals a times e to the I kx plus b times e to the negative I kx, where k equals the square root of 2m e divided by h bar. Region 2 where 0 is less than x less than a, psi 2 equals c times e to the kappa x plus d times e to the negative kappa x, where kappa equals the square root of 2m times v naught minus e divided by h bar. Region 3, where x is greater than a, psi 3 equals f times e to the I kx. The transmission probability is t equals the absolute value of f squared divided by the absolute value of a squared, which approximately equals e to the negative 2 kappa a for thick barriers. This exponential dependence on barrier width is the key to engineering quantum devices. Your smartphone's flash memory exploits this precisely. Electrons tunnel through oxide barriers just 10 nanometers thick. The transmission coefficient t equals the exponential of negative 2 times the square root of 2m times v naught minus e times a, all divided by h bar. For a typical barrier with v naught equals 3.2 electron volts and a equals 10 nanometers, this gives transmission probabilities around 10 to the negative 6th, perfect for controlled data storage. Scanning tunneling microscopy. Scanning tunneling microscopy uses quantum tunneling to achieve atomic resolution. The tunneling current between tip and sample follows. I is proportional to e to the negative 2 kappa d, where d is the tip sample distance, and kappa equals the square root of 2m phi divided by h bar squared, with phi being the work function, typically around 5 electron volts for metals. For a tungsten tip approaching a gold surface, work function, phi equals 5.1 electron volts. Kappa equals 1.02 times 10 to the 10th meters to the negative 1. At 1 nanometer separation, I is proportional to e to the negative 20.4, approximately 6 times 10 to the negative 10th. At 1.1 nanometer separation, I is proportional to e to the negative 22.44, approximately 2 times 10 to the negative 10th. A 0.1 nanometer change, just one atomic radius, changes current by a factor of 3. This exponential sensitivity enables atomic resolution. The result? Images like IBM spelled out in individual xenon atoms, each positioned using the Schrödinger equation. The hydrogen atom solution. The hydrogen atom represents the only multidimensional system with an exact analytical solution. In spherical coordinates, the Hamiltonian h hat equals negative h bar squared over 2 mu times the Laplacian minus k e squared over r, where mu equals me times mp divided by me plus mp is the reduced mass. Using separation of variables, psi of r, theta, phi, equals r of r times y sub l superscript m of theta, phi, we obtain the radial equation, negative h bar squared over 2 mu times 1 over r squared times d over dr of r squared times dr over dr plus the quantity negative k e squared over r plus l times l plus 1 times h bar squared over 2 mu r squared times r equals e times r. The angular equation, y sub l superscript m of theta, phi, equals n sub l superscript absolute value of m times p sub l superscript absolute value of m of cosine theta times e to the I m phi. The complete solutions are psi sub n l m of r, theta, phi, equals r sub n l of r times y sub l superscript m of theta, phi. With quantized energy levels, E sub n equals negative 13.6 electron volts divided by n squared, where n equals 1, 2, 3, and so on. These solutions predicted the hydrogen spectrum with stunning accuracy, validating quantum mechanics. Modern quantum technologies. Modern engineering extends the Schrödinger equation to quantum dots, artificial atoms with tunable properties. For a spherical quantum dot, E sub nl equals E gap plus h bar squared pi squared over 2r squared times the quantity 1 over me star plus 1 over mh star times n squared. By controlling radius r, we engineer exact emission wavelengths for displays and solar cells. In superconductors, Cooper pairs obey a macroscopic Schrödinger equation. I bar times partial psi over partial t equals the quantity negative h bar squared over 2m star times the Laplacian plus qv times psi, where psi represents the superconducting condensate spanning the entire material, quantum mechanics at human scales. Quantum computers directly manipulate solutions to the Schrödinger equation. For a two-level qubit, the state psi equals alpha times the 0 state plus beta times the 1 state. The evolution under quantum gates follows. Psi of t equals e to the negative I h hat t over h bar times psi of 0. We're literally programming the Schrödinger equation. Engineering problem examples. Let's design a quantum well LED. For a gallium arsenide aluminum gallium arsenide quantum well. Step 1. Calculate confinement energy. E1 equals pi squared h bar squared over 2m star L squared. For L equals 10 nanometers, m star equals 0.067 times me. E1 equals pi squared times 1.055 times 10 to the negative 34th squared, divided by 2 times 0.067 times 9.109 times 10 to the negative 31st times 10 to the negative 8th squared equals 56 millielectron volts. Step 2. Emission wavelength. Lambda equals hc divided by E gap plus E1 equals 4.136 times 10 to the negative 15th times 3 times 10 to the 8th divided by 1.424 plus 0.056 equals 838 nanometers, perfect for infrared applications. For a 5 nanometer MOSFET gate oxide, J equals Q cubed E squared over 8 pi squared H bar phi times E to the negative 8 pi square root of 2m phi cubed over 3q E H bar. With E equals 5 times 10 to the 8th volts per meter, phi equals 3.2 electron volts. J equals 10 to the negative 4th amperes per square centimeter. Managing this quantum leakage defines the limits of Moore's law. Experimental verification and philosophical implications. The Schrödinger equation's predictions have been verified with extraordinary precision. Hydrogen spectrum, agreement to 1 part in 10 to the 12th. Quantum tunneling rates, confirmed across 20 orders of magnitude. Atomic interferometry, phase measurements to 10 to the negative 21st radians. But what does the wave function actually represent? This remains quantum mechanics' deepest puzzle. Copenhagen interpretation. Psi represents our knowledge. It collapses upon measurement. Many worlds interpretation. All possibilities in psi occur in parallel universes. Pilot wave theory. Particles have definite positions guided by psi. The mathematics works perfectly. The meaning remains mysterious. The future of quantum engineering. Today, the Schrödinger equation drives technologies Erwin Schrödinger never imagined. Quantum computers solving chemistry problems. Quantum sensors detecting gravitational waves. Quantum communication networks spanning continents. Materials designed atom by atom. This equation, discovered by a physicist who initially doubted his own work, now guides humanity toward room temperature superconductors, fault-tolerant quantum computers, perfect solar energy conversion, maybe even quantum theories of consciousness. The Schrödinger equation isn't just physics, it's the source code of technological civilization. Every quantum device, every piece of modern electronics, every breakthrough in materials science traces back to this mathematical expression. And the most remarkable fact? We're still discovering what it can do. The quantum revolution isn't over, it's accelerating. What applications of quantum mechanics fascinate you most? Quantum computers? Tunneling microscopes? Or perhaps something we haven't discovered yet? Leave your thoughts in the comments. And if you enjoyed this deep dive into the mathematics that built the modern world, subscribe for more explorations of the equations that shape reality. Next week, how Feynman diagrams revolutionized our understanding of fundamental interactions. Until then, remember, you're not just using technology, you're commanding quantum mechanics.